Okay, we're going to continue on here to chapter 9. So in the previous chapters, we talked about kind of grams and moles, and we also talked about equations. And in this chapter, we're going to kind of put it all together and do really calculations from equations. And that's what is sometimes referred to as stoichiometry, using the moles and our balanced equations. So let's get into it here. So I think we saw this a little bit in the previous sort of chapter, but in this chapter for sure, we're going to use a certain type of relationship that we could get from the balance equation there. And from the balance equation, we can really look at the coefficients a couple different ways. We could say, for example, here that there are two molecules of H2 react with one molecule of O2 to give us two molecules of H2O. Really, in this chapter, and pretty much when you do stoichiometry, we will use what again is referred to as the mole-to-mole relationship. And those come really just straight from the coefficients in the balanced equation. So there's no sort of calculating the relationship or anything like that, but is sort of where we get our conversion factor from. So here we can say there are 2 moles of H2 react with 1 mole of O2 to form 2 moles of H2O. And that is sort of the kind of, again, the mole-to-mole relationship. The last there we talked about as well is what is referred to as sort of conservation of mass, because we don't lose any elements along the way in a chemical reaction. They just get basically kind of recombined in different substances. We should have the same amount of reactants and products in terms of the mass of each of those elements. So the amounts of reactants and products is what is sometimes referred to as stoichiometry. And it allows us to answer a bunch of questions that we're sometimes interested in. If we look at an equation and we know how much of a reactant, for example, we're starting with, we could use stoichiometry to predict how much product we should get out in that reaction. We could also do the other opposite of that, which is if we actually know, for example, we do a reaction, or if we want to produce a certain amount of product, we can use stoichiometry to do the calculation to figure out how much of the reactants that we would need to start with. So one important thing about stoichiometry, as we'll talk about here in a second, is it allows us relationships really from reactants, products. We could go from reactants to products. We could go from products to reactants. We could actually just stay on the reactant side and do some stoichiometry calculations between 2 reactants. We could also stay on the product side and do some stoichiometry calculations between a couple of products if we should have a couple of products. So sometimes people get a false sort of understanding of stoichiometry that you always have to kind of do the relationship across the arrow from reactants to products or products to reactants, and you really don't. You can really do it with anyone in the equation. You could do it all with reactants. You can do it all with products. You can't go reactants to products or products to reactants in terms of those relationships. So it is very useful in those type of calculations. Now, when we talk about sort of the units that we commonly come across, I would say moles and grams are very common. But later, when we talk about gases, liters is also a very common unit that we use in stoichiometry, and it can be other units as well. But I would say probably in most cases, it's that grams to moles sort of units that we use. And a lot of what we do is to convert things into moles. So that molar mass, again, is what we want to use there from the periodic table to do it. So the mole method is the idea that we use a balanced equation. We use the coefficients from the balanced equations as the mole-to-mole relationship between, again, anyone in the equation, reactant, product, reactant, reactant, and product, product. So when we do basic stoichiometry problems, they really do sort of boil down to 4 steps. There's a couple extra steps or one extra step here. Because sometimes you may be given a problem where everything's given to you in words. So you may not have the reaction and you may have stuff in words. So the first thing that you want to do is make sure, like we talked about when we're talking about balancing equations, that you get all the correct formulas for the reactants and the products down first. Again, just like you were doing nomenclature, you just start with the right formulas. Then the next thing, which is really in a lot of cases, the first thing that you oftentimes will have to do, because oftentimes you will be given an equation and it may be unbalanced, but in case you're not, you want to get the right formulas. You want to make sure that you balance the equation. And frankly, if you do not balance the equation or make sure that the equation they gave you is balanced, pretty much all your calculations is going to be wrong because it's all based on the equation. So that's like the very first thing that you really should do is balance that equation. Next, you want to take whatever they gave you and pretty much get them into moles. So a lot of times you're given grams and you got to go grams to moles. So a lot of times at this step, we got to go grams to moles. And once again, that is the molar mass from the periodic table. That allows you to do that. And the reason we really need to get everybody into moles is because we're going to then go to the equation. We're going to use those coefficients and find the mole to mole relationship. And that is going to allow us to do the conversion that we need. So really in stoichiometry problems, what happens is in a lot of cases, you're given information about somebody in the reaction. And frankly, you're not that interested in that person, but you're interested in somebody else in the reaction. So you need a way to go from one substance to the next. So really what stoichiometry is, and sometimes people get all freaked out about it, but really instead of going to a table to look up a conversion that allows you to go from one thing to the next, where you get the conversion. So you just kind of use the balance equation as like a conversion factor. And that's going to allow you to convert from whatever they gave you, and you pretty much converted to moles there in the previous step, to what you are looking for. After you do really that step, the next step is to take the moles to some other unit. And very commonly, that is again going to be using probably to grams. It's a very common sort of ending unit. It doesn't have to be grams. They may want pounds or some other unit, but a lot of times you might end up with grams. Once again, there you would use the molar mass on the back end of the calculation. So really, like I said, there's kind of 5 steps here, but a lot of times this part's kind of done for you, I would say in most cases. So really stoichiometry problems do boil down to these 4 steps. You want to make sure you have a balanced equation. You want to convert to moles. You want to use the mole to mole relationship from the equation. And then 4, convert moles to some other unit if necessary. So pretty much if you follow those 4 steps in order, you should always get the right answer, I would hope, as long as you didn't make a calculation problem. What you shouldn't do is go backwards. So if something is done for you, just go to the next step. So I've seen people like they give you stuff in moles, so they decide to unconvert it from moles and then reconvert it back to moles and all that kind of stuff. So don't go backwards, just kind of go forward, and you should be in good shape. So any basic stoichiometry problem, and by basic stoichiometry problem, really you're kind of given just one piece of information in the problem about somebody in the reaction. That's sort of a basic stoichiometry problem. Just follow these steps in order and you should be good. So let's talk a little bit about stoichiometry and how we get those relationships. So let's say we have this equation here and it is balanced. So from this one equation, we could actually get a number of different equalities, and they're sometimes called stoichiometrically equal to each other. So for example, I could say that for every 2 moles, which is the coefficient there of CO, I need to put in there basically 1 mole of O2, which is what the coefficient is for O2. I could also say for every 2 moles of CO that I toss in there, I will get out 2 moles of CO2. And again, these relationships are nothing more than just the balanced coefficient from the equation. And I could also say for every 1 mole of O2, I also should get out 2 moles of CO2. So these are 3 different equalities. Now they are what are referred to, as I mentioned, stoichiometrically equal to each other. They are not equal to each other, as clearly 2 does not equal 1, but they're equal to each other in terms of the proportion of everybody that you need to kind of throw in there. Kind of like when you make cookies, you got to throw so much flour, so much chocolate chips, right, to get a dozen cookies out. That's the idea here. They're sort of equal to each other in terms of proportion that you need for this reaction basically to take place. But because they are technically equal to each other in sort of equalities, like any type of equality that we get from a table or anything like that, we could actually write conversion factors for each of these things. So we could write actually 2 conversion factors for each of these equalities here. So for the first one, we could say that there are 2 moles of CO over 1 mole of O2, or 1 mole of O2 is 2 moles of CO. For the second one, we could say 2 moles of CO over 2 moles of CO2 are 2 moles of CO2 over 2 moles of CO. And lastly, for the last one, 1 mole of O2 over 2 moles of CO2 are 2 moles of CO2 over 1 mole of O2. So from this one equation, this one balanced equation, we actually have available to us 6 different conversion factors that we could use in an actual calculation. Will you use all 6 of them? You will not. You most likely will just use one. So you would use the one that you needed based on the question. But these are all the equalities that you can get from this equation, and in this case, 6 different conversion factors that you can get from the equation. Any questions on that there? So just to show you how it sort of maybe would work. So for example, here, let's just say we produced, we'll go with 10.5 grams of CO2. We want to know how many grams of O2 did we start with? Okay, so if we follow those sort of 4 steps that we talked about earlier, pretty much the very first step is balance the equation, which obviously we do have here, right? So we have the balanced equation, so that is done. The next thing that we need to do is convert to moles. So when we look at this particular problem that I just made up, we could see that the only number that we are given is 10.5 grams of CO2. Would I need to convert to moles in this case? I would, right? Because we're in grams. So here we would go to the periodic table and get the molar mass of CO2. So that is for CO2, we got 12.01 and 2 times 16 there. And that's going to give us 4401, I believe. So from the periodic table, we see that the molar mass of CO2 is 4401. So that is the second step that we want to do in our calculation. We're going to take what was given to us, which was 10.5 grams of CO2. We're going to use the molar mass from the periodic table here of 4401 grams per mole of CO2. The grams here are going to cancel. And if you wanted to get an answer in this step, you could. And I'm going to do that since we're going to go kind of each step by themselves. And I'm going to get something like 0.2358 2, and I'm not going to round too much here, moles of CO2. So that is step number 2, which is take whatever they give you and convert to moles. Again, in a lot of cases, if you're not given it in grams, you might have to do a conversion to get to it to grams, but usually the end part of that calculation is grams to moles using the molar mass. Now, remember here, I'm not really interested in the end about CO2. What I'm really interested in is O2. So this is where the third step and really the big stoichiometry part comes into play. We want to go from or use the mole to mole relationship from the equation. So how do you find that relationship? Well, again, you basically find the two things you're interested in. In this case, clearly we're interested in CO2 because it was given to us, and we eventually want to get to O2. So what we would do is we would go to the equation like we did earlier, and we would find that relationship, and that is this relationship right here, that 1 mole of O2, which is the coefficient, is equal to 2 moles of CO2, which is the coefficient for CO2. This is really the stoichiometry part, but it's really just a conversion. So this is how we're going to go from CO2 to O2. And that gives us our two options in terms of conversion factors. We could either use the conversion factor here on the left or the conversion factor on the right. And in this case, we want to use the conversion factor on which side, left or right? We want to get rid of CO2 and end up with O2. We should use the one on the left. Yeah, so that is what's going to do it. Here we didn't use any of the other conversion factors. We're just using the one that we needed. So the third step would be really the big stoichiometry step here. I'm going to continue with my number from above. I'm going to use my stoichiometry here from the equation, which is my guy there on the left. 2 moles of CO2 gives me 1 mole of O2. So if we do that, we're going to basically divide by 2 in this case. And we would end up with 0.11929 moles of O2. So that was from the balanced equation. This obviously was the molar mass from the periodic table. At this point, sometimes you may be done with the calculation, but am I done with the calculation? In this case, I am not, because I am in units of moles. And in this case, we want grams. So we do have to do step number 4 here, which most of the time you do, but sometimes you don't. So step number 4 is to take the moles, because frankly, at this point, if you did everything correctly, you should be in moles at this point. If you're not, then you definitely did something wrong. And we want to, in this case, convert to grams. It is also important to remember that at this point, I want to use the molar mass for what thing? O2. Yeah, we're no longer at CO2. We just did the stoichiometry to get rid of it. So we want to use it for O2. So once again, we would need to go back to the periodic table. And since there's 2 oxygens, 2 times 16 is 32 grams per mole for O2. So our last step here would be to take the molar mass for O2. In this case, we're going to multiply by it. So 32 grams are going to go up on top. And a mole of O2 here on the bottom. The mole is going to cancel. We're going to times it by 32. And that's going to give us 3.82 grams of O2. At this point, I am going to clean it up in terms of sig figs. And really, the only sig figs in this problem was our original number, which was 3, which means we should probably end up with 3 sig figs when it's all said and done. And that obviously would be step number 4. So as I mentioned before, pretty much all basic stoichiometry problems boil down to 4 steps. Balance the equation, convert to moles, mole to mole relationship, which is the stoichiometry part. And obviously here, if you need to convert those moles to whatever unit you're looking for at the end. Yeah. Yeah, I personally won't round. Truthfully, the department wants you to do this all in one big calculation, which you can. So if you don't want to get an answer, you could just roll from this calculation to this calculation to that calculation, then at the end round. I wouldn't round too much in between because you know you're going to kind of continue on with the calculation. So I would just follow our normal way to the end to round, or like I did here, take it to a good number of digits. Personally, I just kept using the number in the calculator as I went from one step to the next with all the digits that were there. And I would probably avoid rounding too much along the way. Yeah. Yeah, that's usually the best kind of route. Because again, if you do a little bit of rounding at the beginning and then the next one and the next one, you probably will move yourself further away from the right answer. So it's usually good practice. Try not to round. They sometimes say, like we talked about maybe a long time ago, like keep like a few digits or guard digits so you don't round too much all the way. Yeah. Now that when you pull stuff off the periodic table, the traditional way that most people do it is you should take like 4 significant figures is typically what you should use. Yeah. So definitely anything you kind of pull off the periodic table in terms of molar mass, it should always usually be 4 significant figures is usually what you want to use. Other questions? All right, so let's take a look at some here. This is pretty much what we just went over. So I'll scroll it up there. All right, so why don't we try one here? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed by the complete reaction of 5.32 moles of lithium with water? So again, follow those 4 steps. In this case, we'll kind of talk about it here for a second. They gave you everything in words. So this is what we're talking about. Not very often, maybe that you come across a problem like this, but it does happen. You want to make sure you get the right formulas. So lithium metal is just Li. I guess I should get something to write with there. It would be better. So lithium metal should just be Li. Reacts with water, which is H2O, right? To form hydrogen gas. And it's important if you do this right, hydrogen is diatomic. So you want H2 there, right? And lithium hydroxide, which should be LiOH. So again, what I did here is I wasn't concerned about balancing. I was concerned about getting the proper formulas. Then obviously at this point, you should follow the steps. So I'll write them up here one more time. You want to make sure you have balanced the equation. You want to convert to moles. You want the mole to mole relationship. And then you want moles to some other unit. All right, take a few minutes here and see what you come up with. Follow those steps to see what you can end up. Okay, let's take a look. So again, I can't emphasize enough, basic stoichiometry problem, pretty much just have one piece of information given to me, balance the equation. So we need to make sure we do that. So to balance this, you need to lay up some 2s, I think. Everywhere but there, I think, at H2. So I think that should balance it. That gives me 2 lithiums on both sides, 4 hydrogens, and 2 oxygens. So that takes care of step number 1. Step number 2 is to take whatever they gave us, which in this case was 5.32 moles of lithium, and convert it to moles. Do I need to do that in this case? I do not. It's already done. So again, don't unconvert it and reconvert it or anything crazy like that. At this point, we're ready really at this problem to get right into the stoichiometry. So what we want to do is go to the equation, find the 2 things we're interested in. One thing is what they gave us, which is lithium. The other thing is what we're actually looking to find, which is H2. And from the actual equation, we get the relationship that for every 2 moles of lithium that we put in there, we should get 1 mole of hydrogen out. That would give us 2 conversion factors to possibly use in this case, which is 2 moles of lithium over 1 mole of H2, or 1 mole of H2 over 2 moles of lithium. Now, in this case, we do want to get rid of lithium, right? And we want to end up with hydrogen, which means I think the right one here should be the one on the right in this case. So that is going to be our 3rd step, which is we're going to take our moles of lithium. There are 2 moles of lithium from the equation and 1 mole of hydrogen. And that's the big stoichiometry move right there. That is going to get rid of the moles of lithium. So we're basically taking 5.32, dividing it by, not 5, divided by 2 would be better probably. Gives us 2.66 moles of H2 in this case. And that takes care of step number 3. Step number 4 is to convert moles into some other unit. Do we need to do that in this case? We do not, because we're actually looking for moles. So don't go further than you need, right? So we could just put a box. In this case, we did not need to do step number 4. If I did want to get grams, what would I need next? I would need the molar mass of H2, right? So again, we go back to our periodic table, use 2.016 and use that to convert it out. Yeah. It comes from the balanced equation, and that's pretty much where all the ratios for stoichiometry come from. And it's literally nothing more than the actual coefficients that are there. So because there's a 2 in front of lithium, that means there's 2 moles of lithium. And obviously in chemistry, when a number is not written, it's assumed to be 1. So that's where the 1 for hydrogen comes from. Other questions on that? Okay. All right. So again, hopefully you can see step number 1, step number 2, and was already done. Step number 3, and no need for step number 4 in this case. All right. So let's try another one based off of this equation. I think you have as well. Using the same reaction we just talked about, we want to know how many grams of H2 would be formed by 81.75 grams of lithium. Let me give you some numbers from the periodic table. Lithium is 6.941 and hydrogen is 1.008. All right, again, follow those same 4 steps, balance the equation, convert to moles, just one piece of information given to us. And again, it could be a reactant, it could be a product, doesn't really matter. In this particular case, we're going to balance the equation, which obviously we have done previously. So that is all good since it's the same equation. In this case, we're given 81.75 grams of lithium. So we do need to do the converting to mole steps. So our second step that we would want to do here is to take our 81.75 grams of lithium using the molar mass from the periodic table, 6.941 grams per mole of lithium. Will get us, if we again get an answer in this case, 6.941. We'll get something like 11.7778 moles of lithium. At this point, we have now done step number 2. Step number 3, which is really the stoichiometry problem. It is the same relationship that we saw in the previous part of this problem, which is basically a 2-to-1 relationship. So again, for every 2 moles of lithium from the equation, we get 1 mole of hydrogen, giving us our 2 conversion factors that we could use. And again, in this case, we do want to get rid of lithium and end up with hydrogen. So we'll use the one on the right. So step number 3 here, using the mole-to-mole relationship and the stoichiometry here from the balanced equation, 2 moles of lithium on the bottom, so they cancel. 1 mole of H2 up on top. So we'll divide that by 2. Going to give us 5.8889 moles of H2. So that was the big stoichiometry step from the balanced equation. We are now to H2, which is what we're looking for. And as we were talking about in the previous one, in this case, we actually do need to do step number 4 here, which is take the moles now and convert it to grams. Once again, we do want to remember, and a common mistake sometimes people make is they forget they have now converted to H2. So we do need to go again to the periodic table here and get the molar mass of H2, 2 times 1.008. Going to give us 2.016, I think. All right, so taking our answer here, 5.8889 moles of H2. We get 2.016 grams per mole of H2. Moles of H2 will cancel. And we will end up with 11.87 grams of H2 in this case. And that obviously would be step number 4. Question on that. Again, in terms of sig figs, the only number in the problem was the first number, which had 4. So that's why we ended with 4, because really in this, all you're doing is multiplying and dividing. So that's what you would be looking at. What this number really means is this: if you did this reaction and you threw in there 81.75 grams of lithium, everything went perfect in the reaction, you weren't a klutz and spilled anything, no side reactions or anything like that, the amount of H2 that you should get out is 11.87 grams of H2 should be produced in this case. And that number is also sometimes referred to as the theoretical yield. And that is your maximum amount of yield that you should get in a reaction based on what you're starting with and really the stoichiometry relationship. Again, hopefully, again, you can see those 4 steps there. And as I mentioned earlier, you could do all these steps in one calculation without getting an answer in between. And again, if you do get the answer in between, just kind of make sure you take it through a good number of digits before you end. Any questions on any of those steps there? All right, let's try another one here. The ones we just did. Yeah. Let's try this one here. All right, if you had 765 grams of C6H12O6, what is the mass? So we'll go with how many grams, basically, of CO2 would you produce? So carbon is 12.01 on the periodic table, hydrogen 1.008, and our friend oxygen 16. All right, take 3 minutes here. Again, follow those 4 steps. One piece of information. So basic stoichiometry problem. We want to balance the equation. I would say probably in most cases, if you see coefficients, it's probably balanced, which it is in this case. So we got our balance the equation done. In this case, we are given 765 grams of C6H12O6. The second step, right, is to convert to moles, which we do need to do. So we're going to take our 765 grams of C6H12O6. We would need to go to the periodic table there, and that's going to give us 6 times 12.01 plus 12 times 1.008 for the hydrogen, and 6 times 16 for the oxygen from the periodic table. That's going to give us like $1.80, I think. Is 180.2 grams per mole. And again, you would probably round off there to 4 like we did there for our molar mass. We're going to do our second step here, which is using the molar mass as a conversion factor. We're going to put the grams on the bottom so that they cancel. Get rid of that there. And we will end up with 765 divided by 180.2. If we get an answer at this point, 4.24528 moles of C6H12O6. The next thing that we want to do again is really the stoichiometry part. So we're going to go to the equation and find our mole to mole relationship. Remember, it is the thing that was given to you, which was this guy, and it is what we're trying to find, which is our CO2 here. So in this case, once again, just getting the coefficients, it tells us for every 1 mole of C6H12O6 we toss in there, we're going to get 6 moles of CO2 out. That once again will give us our 2 possible conversion factors to use in this problem. And in this case, we do want to get rid of the C6H12. So once again, here we're actually going to use the one on the right would be the correct one. So doing our third step here, using the stoichiometry from the equation, for every 1 mole of C6H12O6, we get 6 moles of CO2. That's going to cancel out our moles of C6H12. So we're going to actually multiply in this case by 6. And I'm just going to write it underneath here, 25.471, and we'll call it 70 moles of CO2. So step 2, step 3. Last step here is we do need to do it, which is to take our moles to some other unit. In this case, we do need to take it now to grams. So that requires us to revisit the periodic table and once again calculate the molar mass of CO2, which we actually did earlier, which again is 12.01 grams per mole plus 2 times 16 grams per mole. Gives us 44.01 grams per mole as the molar mass of CO2. That would be our final step here. Grams would go on top since that is the unit we are looking for. Moles of CO2 would go on the bottom so that they cancel. And that would get us times 44.01. Going to give us on the calculator here 1121 grams of CO2. Now, if we're looking at sig figs, once again, we got 3 there, so perhaps 1120 grams of CO2 would probably be appropriate here. Question on any of those steps? So once again, you should hopefully start seeing that it is, again, those same 4 steps. Balance equation, convert to moles using molar mass, mole to mole relationship, and convert those moles to some other unit here. This once again means that if we dumped into this reaction 765 grams of the C6H12O6, we should expect to get about 1120 grams of CO2, which once again would also be our theoretical yield. A yield can only be a product, so this is why this obviously would be our theoretical yield. Any questions on basic stoichiometry problems? Okay, so I think what we're going to do is we're going to pass through the next example and actually talk about another sort of aspect of stoichiometry. So we're going to skip this problem. If you want to do it for practice, you can. Maybe we'll come back to it a little bit later. All right, so we're going to talk about limiting reagents now, and they're sometimes called limiting reactants. And in every reaction that you do, there's always something that gets used up first in the reaction, and there's always something that you really have plenty of. And in a reaction, the one that gets used up first is the limiting reagent. And the one that you have plenty of there, as we'll see on the next slide, is what's referred to as the excess reagent. And sometimes people call them reactants as well. So why is that important? If we just think about a basic sort of reaction where we take A plus B and it makes A and B, you clearly need both of those things to make the product. So if in this case, the A was our limiting reagent, once I use up all the A in this reaction, is there any way I can make any more product? There would be no way to make any more product, right? Because you need an A and a B to make our product. And that's why limiting reagents are really important. Limiting reagents are always the ones that determine how much product you could produce. So when you're ever trying to calculate how much product you should produce in a reaction, which is like the theoretical yield, you should always do it based on the limiting reagent because it determines pretty much how much product you produce. Kind of like when you buy hot dogs and hot dog buns, right? They give you more hot dogs than hot dog buns, I think, right? You get 8 and like 10 hot dogs in a package. So you're kind of short a couple of hot dog buns. I'm not sure why they would do that other than make you buy more hot dog buns. But in that case, our hot dog buns would be the limiting reagent. Hot dogs would be the excess reagent. You could even, like in that example, figure out how much you would have left over. You got a couple of them left over at the end of the reaction. So the excess reagent, as I mentioned, is again that reagent that you have plenty of. You have some of it left over. And sometimes in limiting reagent problems, they ask you that. They ask you how much of that excess reagent is still there when the reaction is done. So there's oftentimes two very common things that we calculate. We calculate how much product would be produced, and also a lot of times in limiting reagent problems, how much of that excess reagent is still there. So here's an example. If we have sort of girl and guy workout people and they come together to make workout buddies, in this case, we could see we are going to run out of guys here, and that would be our limiting reagent. And our excess reagent here would be our girl workout buddies. And like I said, you could even, obviously we need one of each, right, to make our product in this case. And then we could even see at the end here, we would be left with two of our excess reagents sort of left over. So again, those are very common sort of things that are asked of you, you know, how much you produce and how much of that is left over. Couple of things. How do you know it is a limiting reagent type problem? The way that you know it is a limiting reagent type problem is you're given enough information to get to moles for everybody on the reactant side. So if you think about the examples we just did, we pretty much just had one piece of information given to us. But if you have enough information to get to moles for everybody on the reactant side, that is definitely a limiting reagent problem. And that means that somewhere along the way, you have to figure out which one's the limiting reagent. And there's a number of different ways to do that. We'll talk about a way to do that. But basically, if you're given enough info to calculate the moles of your reactants, of all your reactants, it's a limiting reagent problem. The good news is one approach, which we'll talk about here, is you simply just follow the same 4 steps we did before, except that you have to do one additional calculation to figure out which one's the limiting reagent and which one is your excess reagent. So you could almost do kind of the same approach. We'll talk about an alternative approach as well. So let's take a look at a reaction here. So if we have this reaction, which is S plus 3F makes SF6, and let's just say hypothetically we started with 4 moles of S and 20 moles of F2. We want to know which one's the limiting reagent and which one's the excess reagent in this case. So the first thing is we would still follow those same 4 steps. You would balance the equation. You would convert to moles. And then really kind of right here, you need to figure out which one is your limiting reagent. And then you really could pick up like normal, use your mole to mole relationship and convert your moles to some other unit. So one approach is kind of right there after sort of our normal second step. We figure out which one's the limiting reagent by basically doing a calculation. So let's talk about this. We'll use this one as an example. So if we followed our steps here, we have a balanced equation, which is here. We want to convert to moles, which was already done for us. So we have 4 moles of sulfur. We have 20 moles of F2. So that was already done. So at this point, this is also how I know this is a limiting reagent problem. I could definitely get to moles of sulfur. I could definitely get to moles of the F2. And that is the moles of both of my reactants. So that tells me that this is a limiting reagent problem. So again, if you're given enough information to get the moles of everybody, definitely has to do sort of this calculation. All right, so one approach to figure out which one's the limiting reagent is to take the moles of what you're starting with. So in this case, in terms of what we are starting with, we have 4 moles of sulfur. and we have 20 moles of F2. And you really can pick either one. And what you're going to do is just a small little calculation to figure out if I wanted to use up all of my, say, sulfur in this case. I want to figure out how much of the F2 I need to kind of put in there. Or you could do the opposite as well. So let's take a look at that first. So this is the calculation to figure out which one is the limiting reagent. So I'm going to take my 4 moles of sulfur, which is what I'm starting with. And from the equation, I can see for every 1 mole of sulfur, I get 3 moles of F2. So I'm going to do this little calculation here. And that's going to be 1 mole of sulfur, 3 moles of F2. So if I want to use up all the sulfur, how much F2 is needed? So that's basically what this calculation is doing. So if I do that, I'm going to take 4 times 3 is 12. And what this calculation just told me is I would need 12 moles of F2 would be needed. First off, any question on the calculation? So it's just a simple little stoichiometry calculation between the two reactants. And basically what you're saying is I want to use up all my sulfur. How much of the F2 in this case I need to put in there? At this point, what we want to compare is the amount of F2 needed to the amount of F2 that we started with. So do I have enough? I need 12 moles of it, and I'm starting with 20 moles of F2. Do I have enough of it? I do, right? So I do have enough. And because I have enough, what that means is the F2 would be my excess reagent. And the beauty of this is by default, the sulfur would be our limiting. Yeah, so it would be our limiting in this case. Question on that there. Now, just to show you that it really does not matter sort of which one you pick. If I did sort of the opposite calculation, which is I want to use up all the F2, how much S is needed? So if I did that, I would start with my F2, which is 20 moles of F2. I would use my same relationship, obviously flipped around so everything cancels out correctly. 3 moles of F2, 1 mole of sulfur. So that would be 20 divided by 3, which would be about 6.67 moles of sulfur is needed. In this case, if I chose this, what that basically says is if I want to use up all the F2 there, I would need to dump in there 6.67 moles of sulfur. I would then compare it to the sulfur. And do I have enough sulfur to do that? I need 6 and I have 4. So that tells us the same thing in terms of it's the limiting reagent, right? And by default, that would mean that the fluorine was the excess. Do you have to do both calculations? You don't. You could just choose either reactant. It works the same in terms of telling you which one is the limiting reagent. First off, any questions on that? Now, once I determine in this case which one is the limiting reagent, I want to always use the limiting reagent and the starting amount to figure out how much product. So once I would determine this, I would go, okay, I am going to use my limiting reagent to figure out how much product I would form. And now that I've already figured out my limiting reagent, I could just continue on with my steps here. So using the starting amount of my limiting reagent, I'm going to do now the mole-to-mole relationship between the limiting reagent and the product, which happens to be a 1-to-1 relationship. So 1 mole of sulfur gives me 1 mole of SF6, and I would end up with 4 moles of SF6. I could obviously get the molar mass and figure out how many grams that would be from the periodic table. That would be our, by the way, theoretical yield in moles, right? That would be our theoretical yield of moles. And again, we could do step number 4 and convert it into grams using the molar mass of SF6. Question on that. Now, to finish up on here for today, we also could use this information to figure out at the end of the reaction how much of my limiting reagent would be left over. So if I wanted to know how much of my, excess reagent is left over, I could use the calculation that I did here to figure out which one's the limiting reagent to help me figure out how much would be left over. I know that I am starting with 20 moles of my excess reagent, which is F2. I know from my calculation here to use up all the limiting reagent, I need 12. So if I subtract those two, that would tell me that I should have 8 moles of F2 left over at the end of the reaction, which I could also convert to grams using the molar mass. And now I would know how much of that excess reagent I have left over. I would know from the limiting reagent how much product I should make. Question on that. So it really is kind of the same calculations we've been doing, just with the additional step. You have to do that limiting reagent sort of calculation. And again, you can use either reactant to do it, but you always want to make sure that when you figure out how much product, that you are using the starting amount, so not your answer from your calculation of limiting reagent. Question on any of those steps there. Now, there are multiple ways that you could do limiting reagent type problems. The other most common way of doing it is just to do 2 individual stoichiometry calculations from reactant to product. So from each reactant to each product, just do 2 calculations like we did before, those 4 steps, and you do it for each one. And whichever one produces the smallest amount of product is your limiting reagent and your theoretical yield. So that's the other approach that's very commonly taught. Just 2 separate calculations from each reactant to the product, smallest amount produced, both your theoretical yield and also your limiting reagent. And by default, obviously, the other guy would be your excess reagent. Question on that there. All right, we will lay it up there for today.